Hey guys, welcome back. In this lecture, we are going to understand coin change problem with its solution. So what is the coin change problem? We will be given a set of coin denominations and target amount for which we are going to make change using the given denominations. It is also given that the supply of given denominations is infinite. To make the target amount, you can use any number of given coin denominations. Let's say the target amount for which we are going to make change is 7 and the given denominations are 1, 3, 5, 2. So let's first see the recursive solution. So I think you know the subproblem. The original problem is for amount 7. Then from here we have to go with all the denominations we have. If here we are going for 1, then now the next subproblem is to make the change for 6. The target amount for the subproblem is 6. And if we go with 3, the next subproblem will be having the target amount 4. And if we go with 5, target amount will be 2. And with 2, the target amount will be 5. So with 1, the next subproblem is 6, right? Here again, we have 4 paths. Again, we're going to go for all. Let's have a complete path when we keep on taking 1. So this is how it's gonna go. This is how the problem is going to get divided. Each path gonna stop either when it reaches 0, that means we have got all the coins needed to make that change, or when the denomination becomes greater than the target amount. As in that case, we won't be able to make the change using that denomination. See this call where we have target amount 4. Here we first go for 1, then we're gonna go for 3, and then for 5, and then for 2. But see here, the target amount for this call is 4, and using 5, we cannot make the change for 4 because it is greater than 4. So this recursion having this 5 is going to stop right here. This is how it works. Now shown is the complete path when we choose 1 as the denomination each time. So if we are taking only 1 rupee coins to make change for 7, then we're gonna end up having 7 coins to make change for 7. Too many coins, right? So at each level we are going to try all the options that can contribute to make the change. And then we select the minimum among these options. Here, if we first choose 5, then the next target will be 2. And from here, if we choose 2, it becomes 0. In this case, only 2 coins are needed to make the change for 7, which is indeed the minimum number of coins to make the change for 7. So let's see the pseudocode. We're going to include the coin and we're going to calculate the coins required for remaining amount or for the subproblem, right? So let's call the function minimum coins recursively to get the minimum number of coins for the subproblem. And now in this result, we will add 1 for the coin we have already selected. But before this, we must check that the coin or the denomination must be greater than the target amount for that call. And this whole thing we're going to do for all the denominations available. So we will be writing this inside the for loop. Now this result is going to get overridden each time for each new denomination as we are having this stuff inside the for loop. So the last result we will be having here is the 1 for the last denomination. But what we want is, we want to get the 1 having minimum number of coins, right? So we're going to put a check here that if the new result, which is subresult plus 1, is less than the previous one or not. If it is less than the previous one, then we're going to overwrite the result. So at the end of this for loop, we will be having minimum number of coins as the result. So this is the final result that we are going to return from here. Now talking about the base case is when the amount or the target amount becomes 0. So in that case, we're going to return 0. So we saw the top-down approach, and using this approach, we can avoid recalculating the overlapping subproblems. Here it is showing only 2 overlapping subproblems, but there will be so many overlapping subproblems, right? Which we can avoid recalculating using top-down approach. So we saw the recursive solution and we saw the top-down solution for the coin change problem. Now let's see the solution using bottom-up approach. So in bottom up, we start from bottom right. So here we're going to divide the complex problem into simpler subproblems, and then we start solving them from bottom to reach to the top. And this is how we're going to get the solution. We keep on storing the results of subproblems, and then we use these results to calculate the solution of bigger subproblems, and finally we reach to the original problem with the final solution. So here we have divided the problem into subproblem. The original problem is of making the change for amount 7, and here the smallest subproblem is of making a change of amount 0. Then we have making a change for a total of 1, and then 2, then 3, 4, 5, 6, and then we have the original problem of making the change for amount 7. Now see the options we have. We can choose any of these denominations at the left to calculate the solution of these problems. We must take them in ascending order. So let's start solving these subproblems. The first subproblem that we have is for amount 0, right? And see the first row. For first row, we are only having the availability of coin 1. So what is the minimum number of 1 rupee coin that are required to make a total of 0? We literally need no coin. 0 1 rupee coins are needed to make a sum of 0. So let's fill the cell with 0. Let's go ahead for the next subproblem having the same single choice, which is of 1 rupee coin. We have infinite supply of 1 rupee coin. We can use as much coins as we need, but we cannot use 2 rupee coin, 3 rupee coin, and 5 rupee coin because this row is dedicated for the 1 rupee coin. So what are the minimum number of ways to make 1 rupee coin or 1 rupee target amount using 1 rupee coins? Obviously, the minimum number of coins is 1. We can use 1 rupee coin as the change. So now the next subproblem is 2. We need 2 1 rupee coins to make a target amount of 2. And similarly for 3, for 4, for 5, for 6, and for 7. Now coming to the next row. At this row we have the availability of 2 rupee coins as well as 1 rupee coins. So using how many 2 rupee or 1 rupee coins we can make a sum of 0? 0. We don't need any coin to make a sum of 0. Now next is 1. We just need 1 rupee coin to make a sum of 1. See here, these values are same as the values in the previous row. That means until we get the subproblem with amount equal to the current denomination, we don't have that denomination as an option in the answer. So here we're just copying these two values and putting it here because we're only using 1 rupee coins to form these targets. So while filling the rows, we don't change the results till we reach to the target equal to the denomination. The next target is 2. To make this target, we can either use 2 1 rupee coins or we can use 1 2 rupee coin. And the one which takes the minimum number of coins to make the change for 2 is when we use 1 2 rupee coin. So let's fill the cell with 1. Next, for 3 rupee coin or for target of 3, we can take 1 2 rupee coin and 1 1 rupee coin. Total of 2 coins, which is less than the coins needed when we use only 1 rupee coins. So minimum number of coins is 2, so we put 2 right here. But how we are actually getting this value? So to get this value, we go 2 steps back in the same row, because this is the row for the denomination 2. That's why we go 2 steps back, and then from here we get this value, we add 1 to this value to get this value 2. Now we compare this value with the value in the previous row at the same column. The minimum one, we choose the minimum one and put that value right here. So the formula to get this value is, we get the value, first we calculate amount minus denomination, we subtract the denomination from the amount. The amount is 3 and the denomination is 2, we get 1. So now we see the value present at the index 1 at this row, and after getting this value we add 1 to this value. Now we have to choose the minimum among these two values, the one we calculated and the value that we calculated at the same column in the previous row. Now the next target is 4. We follow the same process. 4 minus 2 gives us 2. At the index 2 we have 1. We add 1 to it, and then we get the minimum among 2 and 4, which is 2. Same for 5, 6, 7. And our next row is for the denomination 3. Till we reach 3, we have to just copy the values from the previous row and we're gonna put them at these respective cells. Now at 3, we have to repeat this process. This is the formula to calculate the value at the cell. So this is how all the cells gets filled, and finally at the last cell, which is for the original problem, we get the final solution. So this is how we fill this table. Now we're going to implement the solution in code, but here it seems that we have taken a 2D array, but we don't need a 2D array to solve this problem. Because each time we calculate the value for the current cell, the dependency is only on the previously calculated values in the same row and on the value already present at the current cell. For instance, if we are calculating the value to be placed here at this cell, then all the cells before this are already having the updated values, and all the cells after this, including this cell itself, let's say, are having these previous values. Now the dependency of this new value is only on the previously calculated value at the same cell and on the previously calculated value in the same row. So we don't need a 2D array.